Every major language model you use today, whether it's a chatbot, a code assistant, or a translation tool, runs on the same core architecture. It's called the transformer. But here is what most explanations skip over. They jump straight into how attention works without ever asking the more important question: why did we need this thing at all? What was so fundamentally broken about the older approach that researcher had to throw it out and start from the scratch? That's what this video is about. And it's come down to three ideas: a problem, a shift, and a trade-off. The problem is why old model couldn't scale. The shift is what replaced them. And the trade-off is the new cost we had to pay for that power. So let's start at the beginning. Here's the question that seems simple but has deep consequences. If a model reads a 500-word paragraph, right, one word at a time, and the meaning of a word 3 depends on word 497, right? The word that come at 497 location. How does the model remember, right? That right there is the root of everything we have talked about. We are going to talk about today. It sounds like a memory problem, and it partly is, but it actually a structural problem. The architecture itself makes it harder to remember. By the end of this video, you'll be able to explain three things clearly. First, why RNN and LSTM type model hit a structural wall. Second, why replacing recurrence with attention was a genuinely a paradigm shift. And third, why that shift created a brand new complexity challenges that researchers are still solving today. And don't worry about the maths. We'll build every single idea from analogy and intuition first. Equation only show up after you already understand what they mean. So let's go back to how things worked before. Imagine you are translating "the cat sat on the mat" into French. The model that dominated this task before, let's say 2017, was called a sequence to sequence model. And it had two parts. You can watch the animation here. On the left side, the encoder read each English word one by one from left to right. After processing the last word, it compressed everything it seen into a single fixed sized vector. That's the orange box in the middle. That's the hidden state. Think of it like cramping entire paragraph onto one post-it note. On the right side, the decoder takes that compressed vector and generate the French word one at a time. Right? Now, here's the important part. That single vector in the middle is decoder's only window into the source sentence. Every bit of meaning, every grammatical relationship, every word ordering, all of it has to fit inside that one vector. Right? For short sentences, this works reasonably well. But two deep structural problems are hiding beneath the surface. One is about memory and another is about speed. And once you see them clearly, you'll understand exactly why the transformer had to exist. Watch this visualization clearly. The bars represent how much information from the very first word survives as we move through the sequence. At position 1, the signal is at 100%. By position 5, it's already dropped below 50%. By position 10, we are down to about 20%. And by position 20, the model barely remember anything about first word at all. Now, isn't a software bug you can patch. This is a structural consequence of how recurrent networks process information. Each step acts like a lossy compression. The hidden state get multiplied and transformed at every single position, and with each multiplication, distant information slowly fades away. Even LSTM and GRUs, which were specifically designed to fight this problem, only reduce the degradation, they don't eliminate it. Here is a concrete case that makes this real. Consider the sentence: doctor who treated the patient in the emergency ward during the night shift on Tuesday was exhausted. The verb was, right? Need to agree with what? Doctor, right? The verb was need to agree with doctor. But there are 14 words between them. Every one of those words dilutes the connection between the subject and its verb. And remember, real world text isn't just 20 token long. Document and conversation can run into thousands of token, and degradation just keep compounding. Now, here is a second structural problem. And honestly, from a practical standpoint, this one might matter even more. Watch the two rows in this animation. The top row is the RNN, recurrent neural network. Token 1 process, then token 2, then token 3, one after the other. Each step has to wait for the previous step to finish before it can start. Now look at the bottom row. That's the attention-based processing. All tokens light up at the same time in one single step. Notice the bottom row finishes while RNN is still working its way through the sequence. Now think about what this means for training. GPUs are massively parallel machines. They have thousands of cores that can all work at the same time. But if your computational is sequential, meaning step 5 cannot start until step 4 finishes, then most of those cores just sit idle there, right? Doing nothing. It's like having thousands of workers but only giving them one task at a time. Matrix operations, which is what attention uses, can be split across all those cores simultaneously. Every core stays busy. That's why transformer train dramatically faster on the same hardware. And this isn't sort of a minor improvement. The 2017 transformer paper reported training in fraction of the time compared to what RNN baselines were. Not because the model was simpler, but because it could actually saturate modern GPU hardware. The architecture was designed to match the machine. Look at this mental model. This is the mental model I want you to carry with you from this video. On the left, you have 8 students sitting in line. If student 1 needs to send information to student 8, the note has to pass through 6 people in between. Each person reads it, maybe summarize a bit, maybe lost some details and pass it along. By the time it reaches student 8, the message is diluted. That recurrence, that's how an RNN works. Now look at the right side. Same 8 students, but now they are sitting around a shared whiteboard. Student 1 writes on board and student 8 reads it directly. No intermediaries, no dilution, no waiting. Watch how all connection pulse that you are seeing they sort of radiate or they pulse at the same time. Everyone sees everything in single synchronized step. That's self-attention. That's the core idea behind transformer. This shift from sequential relay to direct access is the heart of everything. Every token can look at every other token in one step instead of waiting for the information to trickle through a chain. So, no degradation, no waiting, but direct access. And here it's what's nice about this analogy. It explains both the strength and the weakness of the transformer. Direct access is powerful because there's no information loss. But everyone looking at everyone is expensive because that's a lot of looking, right? Well, put number to that cost in a few minutes, uh, uh, and we'll see how the cost sort of comes out. Keep this picture in mind. Now, just a little bit of history. Now, the transformer didn't appear out of thin air. The idea that led to it developed over several years. And let me sort of walk you through the key moments. 2014, the sequence to sequence framework became the standard for machine translation. You had an RNN encoder and RNN decoder, and that compressed hidden state vector linking them. It worked, but it had exactly the bottleneck we just talked about. Everything had to squeeze through that single vector. In 2015, researchers added something clever. They gave the decoder the ability to peek back at the encoder at each output step. Instead of relying on that single compressed vector. This was the attention mechanism, and it made real difference in translation quality. But here's the important detail. The RNN was still doing all the heavy lifting. Attention was just a helper bolted on the top. Recurrence was still the backbone of the whole system. Then in 2017 came the paper that changed everything. And we all know it, right? Attention is all you need. And the key insight was simple but radical. What if we removed the recurrence entirely and made the attention sole computational mechanism? No more sequential processing, no more information passing through chain, just direct token to token interaction computed in parallel. The results were striking: better translation quality and vastly fast training. So the paradigm shift was not about inventing attention. Attention had existed from 2 years before the transformer. The shift was removing the recurrence and making attention do all the work. That's the move that changed everything. So let's look at what actually changed in architecture. The core component didn't disappear, they were rewired. On the left, the old approach. Input tokens feed into an RNN encoder which process them sequentially. Then an RNN decoder also sequentially generate the output. Attention sit on the top as a helper layer. Recurrence is the backbone and attention assists it. On the right, the transformer. The layer looks similar at first glance, but they are wired completely differently. Self-attention layer handle all the interaction between the token. Feed forward layer process each position independently. And crucially, there is no recurrence anywhere in the architecture. Attention is the backbone now. But notice something interesting about the right side. Without recurrence, the model has no built-in notion of word order. If you shuffle all the input words, the self-attention mechanism wouldn't know the difference. It treats the input as a set, not a sequence, right? That's why the transformer needed positional encoding, an explicit signal that tells the model where each token sit in the sequence. We'll dig into exactly how that works in the later episodes. Now let's put some numbers to the intuition we have been building. For model to learn that two words are related, for a model to learn that two words are related, information has to travel between them, right? The shorter that path, the easier it is for the model to learn the relationship. Look at this chart. When the sequence length is 20, right, the worst case path length is an RNN, for an RNN is 19 step. That means if a word 1 and word 20 are related, the signal has to survive 19 separate transformations. The green bar on the right is self-attention. The path length is 1, always 1. No matter how far apart the words are, it's the same. Okay, let's try dragging it to 50. Okay, the orange bar stretches to 49 step, but the green bar stays exactly where it is, 1 step. This is why transformer learns long range dependency so much more effectively than RNN. Every pair of token is exactly 1 step apart, always. The physical distance in sentence simply doesn't matter. And because it's all matrix multiplication, the GPU can compute all those pairwise interactions simultaneously. The parallelism advantage and the learning advantage reinforces each other. And here's the full picture in the table. Path length, the RNN grows with distance, self-attention stays 1. Computational style, RNN use sequential loop, self-attention use matrix multiplication. GPU utilization, RNN leaves most core idle, self-attention use all of them. Everything lines up in one direction. Now here's the part where you might be thinking, this sounds too good to be true. And you would be right. There's no free lunch. If every token attains to every other token, the number of computational grows as n squared, right? Let's drag the slider and watch what happens. See? So you can see, right? When I take it to, let's say, 100, you are computing around 10,000 attentions pair. Well, that's manageable. Let's push it to 200. Right? That's around, let's suppose, 40,000. And at 500, it's around 250,000, right? Watch how the orange curve pulls away from the green line. That's a quadratic explosion. It gets worse fast. Now extend this thinking to a real world scenarios. At n equals to 1000, that's 1 million pair. At n equals to 1 lakh, which is the length of maybe a long document, you are looking at 10 billion attention computations. Memory and compute requirements grow so fast that long context processing becomes the central engineering challenge of the entire field. So the transformer gave us incredible power for learning relationship between tokens, but at a cost that scales quadratically with sequence length. And that trade-off created a question that launched dozens of research direction. That is, how do you keep the power but tame the cost, right? Sort of tame the elephant or lion. Once attention became the core of modern AI, that engineering question exploded across the research community. If attention is this powerful, how do we make it fast and memory efficient for long context? And the answer came from sort of multiple directions. FlashAttention, tackle the problem at hardware level. If it restructures how attention is computed so that so the data stays in fast on-chip GPU caches instead of being written out on the slow main memory and read back. This is now the default in most of the modern training framework. Sparse attention asked a different question entirely. Does every token really need to attend to every other token? By using pattern like local window and strided connections, it brings the cost down from quadratic towards maybe linear, right? Linear attention method use mathematical kernel tricks to reformulate the computation entirely, trading off some expressiveness for dramatically better scaling. And then comes the context extension technique like ROPE and others that are available allow models trained on shorter sequence of to handle much larger longer input at interface time without failing apart. There are a lot of details in, like, we can go through them at later stage, but forget about the details for now. Here's what I want you to take away from this. The Transformers quadratic cost wasn't a dead end, it was a starting gun. It launched one of the most active subfield in deep learning, and the innovations that come out of it now powers the model with context window exceeding 1 million tokens. The constraint became the catalyst. Before we wrap up this episode, I want to clear up 3 misconceptions that trip people up early in their learning journey. Getting this wrong early creates confusion that compounds across every future concept. So let's fix them now. First one, transformer meant only GPT style models. That's not right at all. The transformer came in 3 main flavors: encoder only, that is model like BERT designed for understanding and classification; decoder only, models like GPT designed to generate text one token at a time; and encoder decoder model like T5 designed for tasks where you transform one sequence into another, like translation or summarization. The transformer is shredded architecture beneath all of them. GPT is just one branch of much bigger family. Second, attention solved everything in NLP. No, it solved the recurrence bottleneck, and that was massive, but it created new challenges. Long context efficiency is still hard, as we just saw with the quadratic cost. The model has no built-in sense of word order, so positional encoding scheme had to be invented. And attention alone isn't enough for complex reasoning, which is why modern architecture rely on feed-forward layers, layer normalization, and carefully tuned training recipes on top. Attention was the breakthrough, but it wasn't the whole solution. And the third one, older models are completely obsolete. This is actually a fascinating development. Recurrent ideas are making a comeback. Model like Mamba and others blend recurrence like state tracking with attention like parallelism, trying to get the best of the both world. They can process sequence efficiently like an RNN, but still train in parallel like a transformer. So the transformer didn't end the conversation about sequence modeling. It redirected it into a new territory. Now let's test whether you actually understood what we covered today. I have 3 questions and I want you to pause and think about each one of them before I reveal the answer. Here's the question 1. Why is one-step token interaction useful for long sentences? Here's the key. Long sentence often have critical relationship between the distant word. Subject word agreement, pronoun references, logical connector that span many positions. With one step interaction, any word can directly attend to any other word no matter how far apart they are in the sentence. There's no intermediate processing to degrade the signal. In an RNN, that same information has to survive being transformed at every single intermediate step, and it faded a little at each one. Direct access means no signal loss. That's the advantage. Okay, why does matrix parallel computation suits GPU better than recurrent loops? GPU has thousands of cores, and they are designed to execute the same operation on different pieces of the data simultaneously. Matrix multiplication decompose perfectly into many independent multiply add operation that spread across all those cores at once. Recurrent loop breaks this completely. Step T plus 1 can't start until step T finishes, right? That's hard sequential dependency. While one step compute, thousands of cores sit idles with nothing to do. And attention replaces that entire chain with one large matrix operation that keeps every core busy. The hardware is finally being used the way it's designed to be used. Okay, the last one. What new cost appear when everything attains to everything? Quadratic cost in sequence length. Every token compute an attention score with every other token. For n tokens, that n squared computation. At short length is completely manageable, but for long documents with let's suppose 1 lakh tokens, you are looking at 10 billion attention computation. And that's exactly why techniques like FlashAttention, sparse attention, and linear attention were developed. The power come with a price, and the entire subfield grew up to manage it. If you got all three, you genuinely understood the core ideas of this episode. Drop a comment and let me know which question made you think the hardest. So let's bring it all together. Takeaway 1. RNN and LSTM sequence model had two structural limits: long distance memory degradation that diluted signal across steps, and a sequential processing bottleneck that prevented them from using GPU parallelism. The architecture didn't match the hardware, and it didn't match the problem. Takeaway 2 is the transformer replaced reoccurrence entirely with self-attention, giving every token direct access to every other token in a single step. That's an incremental improvement. That's a paradigm. That's not an incremental improvement. That's a paradigm shift in how machine process sequence. Takeaway 3: massive parallelism, but plus better learning, but quadratic cost. Takeaway 3 is sort of important. This shift unlocked massive parallelism and better long range learning, but introduced quadratic cost that launched an entire subfield of efficiency research. Power and cost bound together. You can't understand one without the other. Now we know why recurrence had to go, but here's something we haven't explored. Attention existed before the transformer. For 2 years, it worked as an add-on onto RNN, and it was already revolutionary, right? In next episode, we'll trace exactly how that classic encoder-decoder attention worked, and why it made such a big difference, and why the idea naturally evolved into self-attention everywhere. That's coming next. If this video helped something click that didn't make sense before, drop a comment. and let me know which part it was. And if you want to follow this whole series from ground up, hit subscribe so you don't miss the next one. See you there.